In this video, I'll show you how I built a custom USB to Loconet interface and how I combined it with a Raspberry Pi and JMRI to build a compact interface for Wi-Fi throttles to talk to the engines on my layout. This video turned out pretty long, so I've put chapter markers in the video description so you can easily skip to the sections that you are most interested in. I built an interface device based on an Arduino microboard to make the hardware connection between the Raspberry Pi and the Loconet control bus used by my DCC command station. I've linked the GitHub repository with the board schematics, layout files and Arduino software in the description below. You can also build a simplified version without all the LEDs on a breadboard. The repository also contains a list of all the required parts. The OLED display is optional. I designed the board in KiCad, a free EDA software that is available for multiple platforms including Windows and Linux. I went with a PCB production service that accepts the KiCad PCB file directly, so I didn't have to mess around with Gerber files. I prepared all the parts I needed for the circuit and then proceeded to solder them to the board. I put the values for all parts on the board itself, so I didn't need to look up what goes where. The first parts I soldered onto the board were the resistors. This way I can just turn over the board and solder without having to worry about them moving while soldering. Resistors don't care which way they are oriented in the circuit, so you can just solder them in whichever orientation you like best. Diodes, however, need to be mounted in a specific way. The marking on the board has a line on one side and the line on the diode needs to be on the same side. There are 3 transistors of 2 different types in the circuit. All the locations are marked with the required type and the devices should have the type printed on their housing, so double check that you are using the correct type for each location. The outline of the transistor package is marked on the board and has to match the transistor outline when it's soldered in place. When I was done mounting the transistors, I proceeded with the capacitors. The 22 microfarad capacitor is exposed directly to the RailSync lines of the Loconet connections. These lines can have up to 26 volts on them, so I chose a capacitor rated for 50 volt for this specific device. All other capacitors in the circuit are connected to 5 volt, so I used capacitors rated for 16 volt for those. The capacitors are electrolytic capacitors, which are polarized. The spots on the board have one half of the circle filled in with white, which denotes the negative side of the transistor. There's also a small plus sign next to the other half. The capacitors typically have their negative lead marked with a white stripe and the lead is shorter than the other one. The short leg needs to go into the hole where the white fill is. I first soldered just one leg of all the capacitors and then turned over the board to make sure that they are mounted flush with the board before soldering the other leg. The next part was the inductance. Like resistors, it can be mounted either way. When that was done, I proceeded with the bridge rectifier. The round marking for it on the board has a dash next to one of the mounting holes. This designates the plus connection of the device. The corresponding lead is also typically longer than the other ones. Much like with the capacitors, I soldered one leg first and then made sure that it sat flush with the board before soldering the other legs. The circuit also has 4 ICs, short for integrated circuits, of 3 different types. There are 2 ICs with 6 legs. These are the optocouplers used to electrically separate the Loconet bus from the USB. I like to use sockets to mount them, because I can easily remove the ICs from the sockets if I need to break up the circuit to test something, but it's fine to just solder them directly to the board. When mounting the ICs, it's important to place them in the correct orientation. The silkscreen markings on the board have a small indentation on the side where pin 1 should be. The packages of the ICs have either a similar indentation or a circle marking near pin 1 or both. The same goes for the IC sockets if you want to use those. Since the board was already populated with all the other components, I used locking tweezers to keep the sockets and the ICs in place while soldering. The next step was soldering on the status LEDs. I decided to use different colors for the power, receive and transmit indicators. The markings on the board have a small protrusion on one side. This marks the anode of the LED, which is typically indicated by the longer leg on the device, or in other words, the short leg needs to go into the square hole. I bent the legs directly at the LED body and proceeded soldering them into place. Again, starting with one leg and then making sure that they sit properly in their spots before soldering the other leg. If you want to use the display, you need to add the 1x4 pin socket. Then it was time to solder the pin sockets for the Arduino. If you can't find the exact size required, you can also mix and match to get to the required amounts of connections. I simply stuck the pin sockets onto the headers of the Arduino and then placed them into the corresponding mounting holes to solder them to the board. The last part was the RJ12 connector for the Loconet. It simply clips onto the board, so soldering the leads is quick and easy and also marks the completion of the interface hardware. After completing the interface circuit, it's time to set up the Raspberry Pi. I went with the 2 GB version of the Raspberry Pi 4. I think it should be possible to get everything to work on the 1 GB version, but we'll need to do some web browsing during the setup and the 1 GB version might struggle a bit with that. In addition to the Pi itself, you'll need an SD card and a power supply. The SD card needs to be at least 8 GB in size to fit the operating system. I went with a 32 GB SD card because it doesn't cost much more. Make sure to get a decently fast card. Most cards meant for video recording should work well. If you're unsure, look for the V30 logo on the packaging. Raspberry sells a compatible power supply and also an adapter from mini HDMI to full-size HDMI. You'll need the adapter along with at least a USB keyboard for the initial setup. The Raspberry Pi 4 is more powerful than previous generations. This comes at the cost of more heat generation. The Pi does not come with a heatsink, so I recommend that you also get one of these stick-on heatsinks. Wherever you're buying your Raspberry Pi also carries these. They're cheap, reasonably effective, and keep the CPU from running too toasty. Raspberry provides a convenient tool to write operating system images to the SD card. It's called the Pi Imager and can be downloaded from their website. I've put a link to the download page in the video description. After starting the Imager, it presents you with a button to select the image you want to install. Click the Choose OS button to bring up the list of available images. The default is the 32-bit Raspberry Pi OS, but we want to select Raspberry Pi OS Other, which will bring up a more extensive list, and then select Raspberry Pi OS 64-bit because it's 2022 already. Then click the Choose Storage button to bring up the device list. It might be a bit confusing to figure out which device is the correct one. I simply wait until now to insert the card into my PC and select whichever new device pops up. Then simply click Write to start writing the image to the disk and wait until the tool is done. This will typically take a couple of minutes. After the image has been written to the SD card, you can remove the card from the adapter and put it into the SD card slot on the Pi. Attach the USB keyboard and connect the Pi to a monitor or a TV with one of the two mini HDMI connectors. Then connect the USB-C power supply to power on the Raspberry Pi. After starting up with the SD card for the first time, the Raspberry Pi will do some initial setup until you're greeted by the user interface and a setup wizard that will ask you to enter some basic data like your time zone and your keyboard layout. It will also ask you to set a new password for the default user. If you leave the password field blank and just hit next, it will keep the standard password Raspberry. It will also ask you for the required data to connect to your Wi-Fi. After you have connected the Raspberry Pi to your network, you can access it remotely. In order to do so, you need to enable the VNC access first by going to the Start menu and then click Preferences and then Raspberry Pi Configuration. Go to the Interfaces tab and enable the VNC access. You will also need to download the VNC Viewer application for your PC operating system and launch it. To connect to your Raspberry Pi, type Raspberry Pi in the address field at the top of the screen and hit Enter. The application will then ask you for the login information. Enter Pi as username and Raspberry as the password if you kept the default password. Tick the Remember Password field so you don't have to type the password again and hit Enter to connect. You should now see the GUI of the Raspberry Pi. To complete the setup of the LocoNet interface, we need to install some additional software. To do so, go to Preferences and add Remove Software in the Start menu. Type Arduino into the search bar and hit Enter. Then select AVR Development Board IDE from Arduino CC and hit OK. You will be asked for your password to authorize the installation. If you didn't change the password during setup, the standard password Raspberry will work. After that, the required software packages will be downloaded and installed. When everything is done, the installation window will close automatically. While the installation is running, you can already connect the Arduino to the Raspberry Pi with a short USB cable. You should see the LED on the Arduino blinking if it's a new device. You should also see the 5V USB LED on the circuit board light up. If you have already connected the circuit board to the LocoNet bus, the 5V LN LED should also light up. The next thing we need is the software for the Arduino Micro sitting on the interface circuit. I have put a link to the release page in the description of the video. Go there and download the latest release as a zip file. Then go to the Downloads folder and unzip the archive. The Arduino IDE requires the INO file to sit in a folder with the same name, so you need to rename the resulting folder to just LN Gateway. Then double-click the INO file and the Arduino IDE should start right up. In the IDE then go to Tools and then Manage Libraries and type LocoNet in the search field. Select the search result and hit Install. Opening the dialog and searching the libraries is a bit slow, so give it some time. When that has finished, search for SSD 1306 and select the Adafruit SSD 1306 library. After hitting Install, it will ask you if you want to also install some other related libraries. Install everything and wait until the installation has finished, then close the dialog. Back in the main window, select Tools from the main menu and then Board and Arduino Micro to select the correct board type. Next, make sure that you have the Arduino Micro plugged into the Raspberry Pi and select Tools, then Port, and then select the entry with Arduino Micro next to it. If you set up the circuit without the display, you can skip the next section. If you have plugged in the display, we need to make sure that the address is correct. You can check the markings on the display to see which address it's using, but that information is wrong on most boards anyways. So we'll use one of the examples shipping with the Arduino IDE to find out the address. The required example project is located in the menu under File, Examples, Wire and then I2C Scanner. Simply click the Upload button in the toolbar and wait for the upload to finish. When the upload has finished, you can close the example project and then click Tools in the menu and then Serial Monitor. The code running on the Arduino will report the addresses of any devices it finds. If it reports the address 3C, you don't need to do anything. If it reports any other address, you need to update the corresponding line in the LN Gateway code. Now you should be able to click on the Upload button in the toolbar and the IDE should compile the software and automatically load it into the Arduino Micro. If you have a display on the circuit, it should display LN Gateway. If you don't have a display, the green LED on the Arduino should light up. The STX and SRX LEDs on the circuit board should light up as well to indicate that the Arduino is waiting for a serial connection. The next step is downloading and setting up JMRI. If you have not installed the Arduino IDE from the previous sections, you might need to install the Java runtime first. Go to Preferences and then add Remove Software and type OpenJDK into the search field and hit Enter. In the list of search results, select Standard Java or Java compatible runtime and hit OK. If you didn't change the password during setup, you can use the standard password Raspberry in the password prompt. When the installation has finished, open the browser and download the Linux version of the JMRI package. When the download has finished, open the Downloads folder and decompress the tar.gz file. Then move the JMRI folder from the Downloads folder to the Home PI folder. Go into the JMRI folder, right-click on the panel profile and select Properties and then Permission, and make sure that the file is executable by anybody. Then close the Properties dialog and double-click the panel proscript to start JMRI. The Preferences panel should come up automatically, otherwise go to Edit and then Preferences to bring it up. To set up the connection to the interface, go to the Connections section and then select Digitrax and LocoBuffer NG. Make sure you select the correct serial interface from the drop-down menu. It should be the same interface you selected in the Arduino IDE. Next, go to the YThrottle section and tick the Start Automatically checkbox. Click Save to save the setup and then restart JMRI. If everything went well, the 4 communication LEDs on the circuit board should start flashing. If you have a display, it should show the data packets being sent and received. Setting up JMRI to start with the Raspberry Pi requires some extra steps. Open the file manager and go to home.pi.config. Create the folder AutoStart with a right-click menu if it doesn't exist yet and go into the AutoStart folder. Then right-click and select New File and create the file jmri.desktop. Next, right-click on the newly created file and select Text Editor. You need to type this into the editor. I have also put the text into the video description. Save the file, close the editor and then reboot the Raspberry Pi. Your Wi-Fi throttles should now be able to connect to the YThrottle server if you are on the same network as the Raspberry Pi. You can also use the Engine Driver app on Android or the YThrottle app on iOS to test the setup. I hope this guide has helped you set up your own little YThrottle hub. If you have any questions, let me know in the comments.